Hi, John here from EPA, and today I'm here to talk about private high voltage networks and what's important to consider when designing them.
Electrical Projects Australia.
A private high voltage network is a high voltage network which is owned and controlled by a private customer. So it's not a utility, it's separate from a utility, it's on a private property and it's run by the customer that owns the property. Usually private high voltage networks are for large campuses such as universities, large industrial sites, or large private residential sites. The reason for having a private high voltage network is that your site is just too large to distribute via low voltage, and you just cannot distribute power at low voltage. You'll just lose too much energy through the losses in the cables. So the first thing you need to do when you're planning or designing a private high voltage network is to determine how much power you're going to need. Next, once you know how much power you need to go to your local energy authority and apply for that power. There will be different processes involved in applying for that, and it usually takes a long time. So I suggest if you're going to do that, to get in early, because it can take up to 6 months for the energy authority to provide that power. Now you have the ball rolling on getting connection to site from the energy authority. You need to start considering what sort of high voltage network you want to install. Like anything, you pay for what you get. So if you wanted to just install something and just thinking about dollars and cents and making sure that you can get the cheapest and quickest network in, usually that's just a simple high voltage network with kiosk type transformers off it. A kiosk type substation is basically a box that sits outside with the high voltage circuit breakers, the transformer and the low voltage breakers all squashed into that one box. However, you might have the need for a more, robust and operable network. You might be, for example, a hospital or a university campus where you can't afford to lose power, and you want that power up all the time. You want the ability to get there and do some switching in any weather circumstance. And to do that, usually you'll go with a chamber type substation, which is basically a room with all your high voltage gear in it. Also, if you're going to go for a more robust network, I would always recommend going with a ring type topology. The next important thing you need to consider is your earthing. Typically, as you've got a high voltage network, any earth fault will try to get back to the start point as usual. However, the start point is out at, usually the zone substation. The start point is directly connected to earth. So if you have an earth fault, basically all the earth fault current will travel from the phase conductor into the ground and travel all the way back through the earth to that zone sub. So when you're considering your earthing, you need to first consider your touch and step potentials. Basically, to do this, you'd first go and you'd typically look at the soil resistivity, and you can do that by testing. You come back into your office and then you run some software and you model what your earthing network typically might look like, and you put your earth fault current in there, the disconnection time of the breaker, and see what would happen with the standard earthing design with a ring buried underground and a few stakes. And if you can't pass your step and touch potentials, and you keep working and iterating until you see that you comply with the step and touch potentials. Those step and touch potentials are actually outlined in AS2067 as well. There's one new consideration which we're coming across more and more, and that's smart grid. Now, smart grid in a private high voltage network is a little bit different to what a utility would consider it. And basically that's because you're a smaller network and you're relying on the utility anyhow to provide that sync point and that infinite bus. Other things that you consider when you're doing a private high voltage network. So there's remote control and monitoring. So you could have a SCADA set up in your engineer's office, your electrical engineer's office that monitors the site. And he could just see the health and the status of all the switches, all the earth switches and the circuit breakers and the transformers, how much load's going through each. You could attach maintenance logs to those transformers so you can see when the next maintenance and service is due on a particular piece of equipment. But when you've got a smart network, and especially now, or smart grid, especially now that you've got a lot of micro generation on different buildings, and if you've got a campus and you've got a private high voltage network, you'll have multiple buildings. And as you're building new buildings today, generally we are installing solar PV in those buildings. Now, one thing you could look at is that for that particular building that you're installing, rather than relying on the power factor correction, which is some really big high voltage capacitors sitting up at the top of the network, you can use at certain times of day when you're generating enough, you could shift the current coming out of your PV solar inverters to correct for the inductive loads like the air cons and stuff that you have going on there, and rely less on the big capacitors at the front of site. Another thing you could look at is if you've got a big HVAC plant and you've got a big motor on that plant and you're using a VSD to control that motor, you're going to get a lot of current harmonics drawing from that VSD. Now, in turn, that will cause a lot of voltage harmonics in your network and affect other buildings in your network. Now, you could look at perhaps injecting the inverse harmonics into your network from your solar PV inverters or whatever generation you're using inverters to smooth out that harmonics, and that will then cause less issues for the other buildings around you. And finally, on large private sites, you can commonly have backup generators, and they're just there. If the utility drops out, you've got a big backup generator sitting there ready to power up. Now, you could potentially have that generator sit in there, and during some peak loads, you could look at maybe starting up that generator and just lock the top off that load. At EPA, we provide a number of high voltage design services, including earthing design, load flow analysis, private high voltage design and documentation, HV safety management plans, and high voltage master plans. So if you want to learn more about high voltage networks and what we can provide you at EPA, go to our website at electricalprojectsaustralia.com.au and scroll to our high voltage page and have a look through it. And we have a couple of different calculators and a bit of a brief for what we can provide you. So if you like this video, give us a thumbs up, please subscribe, and I'll see you soon. Thanks.